good day, class. So today we're going to go over Le Chatelier's principle. So we're going to, for today's schedule, we'll review what we did last class because it's very important for today. We'll show you a little intriguing video to get you thinking about about the class. We'll go over the principles of Chatelier's principle. We'll give you a worksheet and then we'll go back to the video. So what we did last class. So what is chemical reaction equilibrium? The equilibrium means that the reaction can go forward as much as it can go backwards. So that means that both products and reactants will be used equally and at equal rates. So what effects can factor in the change of an equilibrium in a reaction? So that would be a temperature change, the pressure change, or a concentration change. And quick reminder, how do we balance an equation? So if I have water and I want to turn it into its components of hydrogen 2 plus oxygen, how would I balance this? So you can clearly see you have 2 oxygens and you only have 1 here. So to balance this out, you'd need a 2 here. Afterwards, we have a 2 and a 2. We only have 2 here, so technically we need 4. So we'd have to put a 2 here. This would be a balanced equation. So on to our little video. I should have opened this before we did this.
It's okay, it's okay. You can check yourself. It's like we're all our first years.
There we go. So we're going to show you a fun little video. And now it's just going to start playing again. So as you saw, there's 2 reactants. So there's the red one and the white one. And right now it's normal that the questions I'm about to ask you, you're not like fully sure what the answers are, but we're going to go back to it at the end of the class. So what are your hypotheses on this video? So what I mean is, where do you think the color blue came from? And once again, you're not supposed to know, so there's no wrong answers right now.
Are you asking for the country? Like,
So like,
where?
what was the
Oh.
video? How did it
There's no wrong answers.
Okay.
They mixed.
So the combination of both,
Yeah?
Reaction.
I don't know.
the reaction. Okay. And did you notice anything about the speed at which both reactants were being used? We can play the video again.
Yeah.
Yeah.
Please. It's kind of fast.
Yeah.
Feels like the white is attacking the red.
Is what?
The white is like attacking the red.
So the white seems like it's attacking the red, so
Yeah.
maybe it's being used quicker.
Yeah.
But okay, we're gonna go back to it at the end of the class. So we're gonna keep.
So Le Chatelier's principle. Le Chatelier's principle is mainly just to know in what direction a shift is going to cause and what effects it has on the concentration. So there's 2 types of directions. There's the forward reaction and the reverse reaction. It all depends on your perspective. If you as your reactant, then this would be your forward, and this would be your reverse. It all depends on perspective. You can switch this around and it switches the side of the reactions. So, taking that in mind, if you apply the constraints of specific factors like concentration, if you were to change the concentration of a reactant, what effects would it have and what would it do to the directions? If you were to change the concentration of a product, what would it do and where would it go? So it all depends on ratios and also on the directions and mole fractions. So if you take the reactants, let's say we go back on this equation. These are going to be your reactants, those are your products. If I change the concentration of this, let's say I put more water, then what's going to happen if I want to keep a balanced equation?
You have to add some on the other.
So what is going to happen is the reaction is going to favor the forward reaction to balance it out. Let's say I take out water. So let's say I go down. What is it going to do? They want to keep a balanced equation. So let's say I have less water than on this formula. So it's going to be the opposite. They're going to create more water. So they're going to try to balance it out by making more. So the reverse reaction is going to be favored. And next effect is going to be pressure. So pressure only works if you have gases. The goal when let's say an increase of pressure is done, the goal is to reduce the overall pressure. Pressure is seen as how many molecules hit the container. So if you have a smaller container and more molecules, there's more moving around. If the container is bigger, there's less moving. So it's all a perspective. If I have, let's say, A gas plus 2B gas, it's in equilibrium. I have C gas and D gas. If I increase the pressure of the overall container, my goal is to favor the reaction that will reduce the overall pressure. If it's a condition of how many moles interact with the container, that means I have to reduce the amount of moles. Which side would be favored?
The first one?
So you think we'd go in the forward direction? Meaning we take this and we make this?
No.
Or we take those and make those?
Those and those.
So it'd be the opposite, because you have 3 on this side and you have 2 on this side.
Oh.
So there'd be less pressure if I favored only the 2 molecules over the 3. So that's what pressure would do. So you find the number of moles, so I have 2, 3 and 2, and then I find the direction. So I want the least amount of moles, I'll go with the 2. So I know that this reaction will favor the forward if I increase the pressure. Now if I was to decrease the pressure, there's more room. So they want to have more moles. So what would happen? You'd do the opposite. You'd go backwards. So instead of taking 2, you'd take 3 because there's more room. So they balance it out by taking more space. Now the last restraint you can do is temperature. Now temperature is all about finding which is exothermic and which is endothermic. Exothermic only means that energy is given off at the end of a reaction. Endothermic means heat is added. So if I take this equation and I say that the enthalpy is negative 250 kilojoules per mole, that means that my reaction is endothermic. That means we're giving off energy. That means that the whole process is making energy while giving itself. So that just is another way of saying that heat is a byproduct on this side. So if the goal when temperature is added is to reduce the amount of heat. So if I add energy, let's say in the forward direction, so let's say I was added 500 here, kilojoules per mole, then my goal would be to reduce the amount of heat. So what would I do? Which direction would be forward? Favored, not forward, favored. Yes, because basically we added too much energy that the reaction doesn't want it, so we'd favor the exothermic direction to reduce the heat. But if we had removed heat, which means we've added more heat here, that means there's too much heat on this side, meaning that we favor this direction. So when we decrease the heat, so since I added it on this side, we have decreased the heat, we favor the exothermic direction. Okay. Yeah. No, I did it backwards. Sorry. Exothermic is down here. Something went wrong. Yeah, that's it. Okay, sorry. So since I added heat over here, which is in the exothermic direction, if we take it from this perspective, it makes it the endothermic direction when we want to make it equilibrium. I'm so sorry, I messed it up.
It's okay.
I was so confused. Okay, so now we are going to give you a little worksheet, which for some reason I left over there, for you to work on in groups of 2 to 3. So I'll have some of you working on the first 3 questions, and some of you working on the last 3 questions. Those first 3. Last 3. If you have any questions, feel free to ask. We are here to help.
And we're gonna give you like 5 minutes just to start the worksheet, and no worries if you're not done.
On va 2 ici. Donc là on a 6, donc là on mettrait 2. I used to be good.
It's fine, no problem.
2 il y a 12 ici, donc on met 2. Ça fait 8.
C'est quoi? Ça fait 8. Là, on en a 4.
On met 2.
Attends. Là, du coup, on a mis 2. Là, on a tous. Donc là, on a 4.
Non, mais
encore un décroché.
Ça va ensemble.
Oui, mais on a dit qu'on faisait x2, ça. Donc lui aussi, il est x2.
Maintenant on a 2. Il y a 2.
Mais ça, c'est une
Ça va pas ensemble?
Non. En gros, celle-là, on l'a éclatée.
Le plus, ça se sépare en fond.
Oui. En fait, c'est celle-là, on l'a éclatée en 2 degrés. Et là, c'est l'inverse, on a les 2 molécules. Donc là, on a 2 fois 2, donc on a 4.
I thought I
On a
could
4.
keep.
Ah non, je vais vérifier, je vais vérifier. Là, parce que là, on a 2.
Very much better.
You're welcome.
C'est pour ça que j'avais fait
Non,
là,
en fait,
moi,
non, non, là c'est 0 et là c'est 0. Parce que là t'as 2 C, donc là t'as 2 C, là t'as
Moi, les deux, je le fais là. On est ici. Ah oui? Et là, il y a 2 C, là.
2 C, 2 C. Donc ça c'est
Un, deux, là.
Dans un sens, tu mets les bas. Donc là on a 2 C. Donc ça va être 2. Et après on a
Non, un 8 H.
8 H. Donc là on a 2. Et là celui-là on ne bougeait pas. Donc là si on a 2, ça veut dire que je prends encore 6. Donc là il faut 3. Quoi? Ça,
Pourquoi 6?
parce que t'as 2. Regarde, d'un côté t'as 2 C et t'as 8.
Faut l'en faire 8 H, je comprends avec les deux.
Non mais je vais te montrer pour ceux qui regardent. De l'autre côté, on a 2 C,
2 H.
on a 2 H et encore 2 H. Celui-là indivisé n'est pas bougé. Donc ça fait C, H, 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 H. Ok? Donc là, il nous manque 4 H. Donc, il nous faut encore 2 fois 2. Donc là, tu vas ramener. En fait, tu veux ça fait déjà 2. Je suis pas faite pour prof de chimie.
Arrêtez à 17 ans. On va la dire aussi. Figure 1. Like endowment
En
for
bas,
the product and reactant.
donc là, on a 36.
Ça va baisser la température.
Pas les réactions,
Ah, faut choisir A, B, C. C'est pas le réacteur.
Oui.
pas de question.
C'est ça.
Moi, je fais pas
C'est un autre, on va voir par là.
J'ai ça dans le site. Mais dans le fond,
C'est soit lui, soit lui.
Oui, ça inclut tout ce qu'elle fait. Attends,
Putain, non.
Okay, so no worries if you're not done yet. I'm not expecting you guys to be done. We're gonna start going over the worksheet slowly. And we're gonna go over it as a class, so feel free to tell your opinions too. Before going over the worksheet, I just wanna do a little formative assessment. I just wanna ask you guys, what part did you find most challenging in this worksheet? So you had the first 3 questions, so I'm gonna start with you guys.
The second one of the first question.
Okay, so this one,
Yes.
so what exactly did you find challenging about?
Well, we didn't know the proper amount of H. I
Okay.
couldn't find it.
So you had a hard time with the calculations?
Yes, you did find it. I did.
Okay, no worries. And for your part, is there something in particular that you found most challenging?
Yeah, I think like the same one. I just looking like at every component that it's on to really figure out the amount. Because when you look at it as a whole, so like you forget a few numbers.
Yeah, so it gets confusing quickly.
Yeah.
I see. I feel like both of your questions or parts that you found most challenging are things that with practice you're gonna develop, like it's gonna become easier. Like it's not easy, but you're gonna have an easier time doing it. So my other question was, which part do you believe needs more development? So I think overall, a lot, like a bit more practice. And
Yeah, but we're not students, so there's that to keep in mind.
yeah.
I think if we were like in a real classroom or like real background knowledge, I think we could have been good.
I'm sure you're right. So we're gonna start going over the handout. So
For number 1, how'd you guys do it? So what'd you do for FE?
Okay, that's what
We put it 3.
Why'd you get the 3?
on the other side, because on the other side, yeah.
Because there's a 3 right here,
Yes.
right?
And
So
because
if you have 3 FE, then what'd you do for the oxygen?
we put it 2 because on the other side of the equation there's 4 of them.
Yeah, so if you have a 2 here and a 2 here, you multiply those, you get 4, that's good. So what'd you do for this one?
Okay, so we said we put it a 2 before the.
Put a 2 here,
4.
because there's a 2 here.
Yes.
And so after that we counted the H, so because we have 8 one
you have
side.
8 H here,
Yeah, so there was 2, and so
so
we
you
put
have
it
2 here,
a 3 before the.
you put a 3
so
here,
there's 6.
then you have 6
2
here.
plus 6 equals 8.
So then what would be this?
0.
Zero.
Nothing.
1. Yeah.
It'd be 1, because if
Oh,
it's 0, then there's no product. So this would have to be 1.
Oh. I thought we could put nothing.
You can put nothing, but don't put a 0.
You
You can leave it blank, but don't put a 0. Okay,
The other thing is we don't have molecule.
Oh. That's my bad.
so for question 2, you have to base it off figure 1, which would be this. So question 2 is if you increase the energy in the endothermic direction, what would it do?
We said D. So the reaction favors the reverse reaction. The concentration of the reactants will increase.
Yes, because these.
Okay.
Sorry. Yeah, because if you add more heat on this side, and you look at this direction, there's more heat, so it's going to favor this side more.
Yeah.
And since those are seen as our reactants, then this would increase. If you look at question 3, if we add energy in the exothermic direction, what would it do?
This is C.
Say, read it.
The reaction favors the forward reaction. The concentration of the products will increase.
Exactly. Because if you add more heat over there, that means this was created more to compensate for the heat over there. So you add more product. If you look at question number 4, how did you guys, which direction would this reaction go if I was to increase the pressure?
Oh, we said forward.
Forward. So how'd you guys go about? So how'd you guys go about finding the direction?
Because like in this one there's gases, and the other one it was vapor. But the first one had heat, and then the other one.
So heat does not play a role in pressure. So the way you would go is you calculate the amount of moles. So there's 2 and 1, so there'd be 3 on this side. And on this side, there'd only be 2. So if you increase the pressure, you want to go to the side where there's less, so you'd go forward. Screen time. If you look at B,
I would say
reverse?
Yeah.
Why?
because there are more molecules on. No, no, of course, because there are more molecules on this side than that.
Yes. If you were to look at the whole scheme, there'd be more molecules on this side. But since we only focus on gas, since there's 11 and there's only 8, this will also be in the forward direction. If you look at 2NO4, 2NO2 and 2NO2O4. Which side would this one go? Is it really?
We will go reverse.
Why?
Cause there's N2, O4. I think.
Because of the mole ratio. So here we have 1 mole of N2O4, and here we have 2 moles of NO2. Yes?
We don't have the same equation on.
No, I know.
No, I-
That's why you guys focused on the first three.
I was so confused.
Well, you guys have the same thing. The only thing that's been omitted is the gas part. Except the last one. The last one's different. Yes. You have a HI.
Yeah.
So since this is 1 and this is 2, you'd favor the reverse reaction. So if you look at number 5, if the products of the reaction is increased, which direction will be favored? So which direction is that? Yeah. So what would happen to the product, the reactants? The concentration would increase to compensate for the other ones. If you go on number 6 and you increase the concentration of the reactants, it will go forward to compensate. And what would it do to the products? The concentration will also increase.
So we're gonna like close the class or finish the class by going back to the video we saw at the beginning, and we're gonna give you another chance to like analyze it and say what's your hypothesis on it, and then we're gonna give you the answer of like what's going on. Okay. So we put the second reactant in. It's a really cool video, honestly.
I wanna do it.
So when we asked you at the first, what speed do you think the reaction went at? What we were really asking was what the concentration played effect on the reaction we see there. So if you look at the cobalt, which is the red part of the reaction, and the sodium, we look at the cobalt chlorine, which is the red, and the sodium hydroxide. You see 2 concentration used as reactants. So when we asked you about the speed, now think if I added more sodium to the mix, what would it do? So if we look here at the end, you can clearly see there's more red left and we don't have any more sodium. We can state that the blue part would be the products. So if I increase the sodium quantity, which is the white, which is no longer there, what would happen? If I add more of the sodium chlorine, what would happen to the reaction overall?
Will be faster.
Not faster.
Maybe the red part would have gone to the other side.
Okay. I'm not saying it clear enough. Do you have the black pen? I don't know what it is with the black pen.
Would it be like more concentrated?
What?
Would it be like more concentrated? There would be more.
Which concentration would increase? You're getting it. Which concentration would increase?
The product.
Yes. So you'd have more
More
of
blue.
the blue.
Okay.
Exactly. So if I was to increase the sodium, I'd use up more of the cobalt, thus resulting in more blue in the middle, which is the cobalt reaction with the citron. So if,
So the white became the blue?
The
So
white and red
basically-
became
oh,
blue.
okay. When you look here, I have NaH plus the cobalt chlorine. So that's my red, that's my white. Now when they react together, what I get is a salt, which is NaCl, which has no color whatsoever. What creates the blue is the cobalt hydrogen. So if I added more of the NaCl, I will use up more of this, thus creating more of these, resulting in more blue. If I ask you to decrease the cobalt, let's say I didn't touch anything and I decrease the cobalt chlorine, what's gonna happen?
There's gonna be less product.
Well, if you look at the end, it won't do anything,
Okay,
because
there's some left.
at the end, we still have a little bit of the red left. So it won't change if I decrease it to equal amounts. Because right now we have it in excess, that means there's too much for the reaction to continue. So, if I was to increase the pressure, it's a water drop, but let's say it's in a vase or a container. If I increase the pressure, what's gonna happen?
It's gonna be condensed.
Okay, does it change anything for my formula?
No.
You say no? Why, Diana?
It can stay the same, but just the place of the container is.
So if pressure wants to go towards the lowest amount of moles, if you look at this, would it change? No, it wouldn't, because I have 2 on this side and I have 2 on this side, so the pressure won't change anything.
So I think that for this class, it's gonna be enough. I know that was a lot.
Yeah.
And don't worry, we're gonna go over it next class again, and it's gonna become simpler, because I know it was a big chunk of information for the class this morning, but overall you guys did a great job, and if ever you have any questions or whatsoever, feel free to come ask us during recess, and you have our office appointments on the door. So yeah.